check. Sweet. Okay, so we're recording. All right, so Connor here. I just want to do a quick check-in, show some little bit of progress on some doodling with the Warbler. I want to talk about a few things real quick. Talk about some of the design decisions and my transition to SolidWorks. So, quick background: I started never really using SolidWorks. Never had to support a computer with the EAA trial all the way back when. And never really had a need for it. I ended up turning to Onshape after the Dark Arrow guys recommended it, and it does a lot of things really well. Like for example, you can actually extrude a spline as sheet metal, so that comes in handy. Now we can't put a 3D sketch. There are no 3D sketches in Onshape, so what we end up having to do is we have to take a we can't even drill a hole actually in a flattened sheet metal piece, but we can draw a circle and extrude it. And that's what I've done here. Now it does some funky things because look at how, actually this is the bottom piece, sorry. So that's actually, yeah, sorry, it's the bottom piece. But so the way around it is you gotta draw it on the flat part, and it's not as convenient. It also does some weird stuff, like you can't, SolidWorks is the only package that allows you to have a flange around a curved edge on sheet metal. Other CAD packages don't really do that. I'm hoping they will in the next few years to try to compete feature-wise. So those are some quirks. I try to get around that in Onshape by doing tabs, and a lot of people don't feel comfortable with tabs. That's fine, I get it. After looking at the Zenith kits and really thinking about it, and watching the home built help videos, there's really no reason to have tabs. Flanges are fine. You know, as long as you draw your center line and line up, it's not that big of a deal. So I moved away from those. There were also, those little tabs were killing my rendering performance. I was starting to just kind of hit the brick wall in terms of performance on Shape. So another thing, let's go take a look at the fuse. Fuse, I was trying to draw everything. Onshape really wants to encourage you to draw top down. And, you know, if you're using bottom up, it's whatever, but you start having problems with all the flange alignments. It's much easier to draw bottom up and then assemble it if you're doing all of these flanges fitting together. And the other issue with Onshape was that I didn't have weldment profiles, and that kind of got tricky for things like here. There's a glitch where I've patterned this part, and you can see it's actually in plane with the skin over here for this angle, and the others are not in plane. It actually raises above it, so that's a weird glitch. And I was just kind of getting fed up with that. So moving away from that, actually, real quick, as a design decision, I just want to point out we're using GA30A 418. It's very fat airfoil, gives us lots of spar depth, 10-inch height spar at the moment used for calculation. So it's plenty thick, nice and stable. Constant chord wing, gets good stall characteristics. So let's go take a look at SolidWorks. We haven't really moved anything in SolidWorks. Don't have any made. I'm just trying to draw parts like crazy. You'll notice like the motor mount is not finished yet. It's fine. I temporarily have, this was at an angle for the firewall, and that's why the gear leg is here, but it's not at an angle because I wanted to see, trying to figure out landing gear geometry, because you know I'm trying to make this as versatile, accessible as possible. If you've ever seen a Sonex motor mount, it's a giant pain. If you've ever had to remove a Sonex motor mount, you know how much of a pain it is, not only to build but to remove. So trying to simplify some of that. So let's take a look at some of the nice things about SolidWorks. Even though this isn't finished yet, this is very rough. It fits a little better towards the bottom-up assemblies. Again, here weldments, we can have different weldments, even though it's a pain to have custom weldments. You can do it. So like here, I've got these 1-inch extrusions. Then I've got these bent L angle here. These are all weldment profiles. And this is nice. This is going to give us a good cut list at the end. So we can take 8-foot sections of our angle, bend it, and then we've got a chop list. We can do all of that. One of the important factors to building things fast is that we don't want to have more form blocks than necessary. In the original way, I thought to do bending, because I really did not want the builder to have to buy an 8-foot bending brake, is to make the channel a common size. So if you go to, say, Home Depot, and you go pull like a standard, oh, please don't track me, not a 2x4, a 1x3. Your actual size here, I know this is not a finished piece, something like a poplar board. The actual size here is 2.5 inches thick. So you route the edges, you drill holes about every 6 inches in the middle, and then hammer over. Now, getting that over an 8-foot length, I mean, obviously that's not ideal, but if you're trying to avoid buying a $3,000 brake, it makes a lot of sense to go buy $20 worth of poplar board and get 2 of them, and then you've got an 8-foot bending brake essentially that you hammer over. I kind of stayed away from this idea. What I'm looking at now is that Mittler Brothers makes a really nice little tiny 22 gauge brake that comes in a 96-inch length. It's about $2,200. It's like $300-400 to freight it. The way you get around this, because traditionally you're not supposed to use these, it doesn't have a bending radius, right, for aircraft use. So the way you get around this is that first off, it comes with a upper radius bar, half-inch upper radius bar. So that radius is obviously going to be too large. I mean, you could theoretically use it if you wanted to. So you've got 2 options. You can either manufacture a new bending radius bar, which isn't that big of a deal if you have a welder, or you can 3D print essentially 10-inch sections, 96 inches. It's divisible by 8, so you could print 12 inch sections, and that's going to fit on a standard 3D printer bed. What's 320 millimeter to inches? It's oh yeah, you're fine. So you could do that and print a shoe, which is a good option. Doing a solid infill, it should work just fine. Of course, the only issue, I still haven't been able to try this. This is an in theory thing. In practicality, I haven't been able to try it. The only thing I can think of that could be an issue is attaching it and keeping it permanently on there. I mean, you might just as well glue it down like with hot glue and remove it. Although that's a terrible idea. You shouldn't do that, right? Because eventually, after like 1,000 bends or so, couple hundred bends, right, the plastic's gonna wear out. So let's go back to SolidWorks. And so these, I'm still trying to think about channels and common sizes. If you're curious, that does retain, because I'm trying to keep this panel to 8 or 10 inches, which is trying to keep that in mind with like a 1x8, 1x10. So yeah, it looks fairly similar. Seating layout, that's a good one to talk about. Seating layout, traditionally there's like a pan, there's seat support ribs like on a Thatcher CX4 or on the new Sonex Model Bs. That I don't necessarily like, and the reason why is because it makes accessibility a little difficult. You've got to have all of these little quick nuts. What are they called? Zusa? Is that Zeus fasteners? It can be kind of a pain to install those. I really like the Zenith method where it's kind of slingy. It's not drawn here, but that's a little preferred. And it's, again, like it's hard to visualize because there's just not a lot going on right here. But one thing that's important, I guess, methodology wise, is that this length right here, uh, it's listed at 96. Oh, that's because it's not this. All right. So this length right here actually has to be less than 96 inches to accommodate that brake, because you can't have a bend that's longer than 96 inches. Everything has to fit on that 96-inch brake. So that has to be trimmed back. Not a big deal. Let's see here. The skins, the way the Davis DA2 does it is that there are several more bends, and I'm trying to keep that down as much as possible. One of the things we could do, put a doubler right here of bent angle on the other side. but really it should just be panel, panel, panel top, panel side, panel bottom, and mirror. And the reason why is because you've got lots of flat sheets, less bends. Uh, we can drill, we can have pre-drilled holes and then back drill to drill through the flange. It should be pretty easy to get good accuracy with that flange, right? So this starts to look a lot like any other design, like a Sonix or a Zenith, where those turtle ducks are just curved. This one is flat, and so the reason why you would do that is because the most expensive part, single-handedly probably, is your canopy, right? Because especially if you have international orders, they always require that you buy two, which is kind of silly. Going back to the old way of having flat panels makes a lot more sense. You can walk into mm, good coffee. You can walk into like a hardware store, buy the really nice Lexan for your front place. It's crash resistant, but you lose your optical properties, and then buy an acrylic. And you ideally want, but the problem is I haven't tried this, but ideally you want the radius in the front end to be gentle enough that you can cold bend it, so you don't have to apply heat. Now, acrylic is really brittle. I'm not saying this is a good idea. I'm just saying it's an idea. That's kind of the plan at the moment. Until I can get some real world results, then I don't know if that'll actually work or not. But even applying a small amount of heat to get a very large radius bend shouldn't be that big of a deal, as opposed to putting the whole thing in an oven and squeegeeing it or pressing it out to a traditional shape, or blowing it even is more difficult. Building that oven is just something that's kind of beyond what most home builders want to do. Last thing I want to talk about is the landing gear, and the reason why I'm opting for a spring steel gear. Sonix has titanium. It's hard to find titanium. So, if builders can't find it, they don't want to build it. You can find 4130 fairly easily, right? Even if you have to order from Spruce, shipping is murderous, but you can get it. You can call up aerospace manufacturers and metal suppliers, and they can get it to you. So that's a better choice. With that, you've got the springiness. I get it. Some people don't want it, but uh, bending, what is it, 3/4 inch plate? First off, cutting 3/4 inch plate out of 6061, like on a Zenith, or say like the Thatcher series, it's just not practical for an average person. They're not going to go out and buy that giant press, get it aligned properly. It's just kind of silly to ask them to do that. But it's not terribly silly to ask an average Joe to buy the pre-welded, or if they have competence, not confidence, if they have competence, to ask them to practice welding tubing, learn a new skill, and be able to weld an engine mount and a gear leg. It's just substantially easier to have one piece of constant width tubing, and you can CNC cut a jig to make sure that your alignment is correct. That's less of a big deal. And like the Vans, Whitman, Tailwind, all of them, Sonics too, but again, they use titanium for the gear leg. It all goes into the motor mount. It makes structural sense. It's a good heuristic, if anything, to just start there. So that's progress. One thing I want to complain about real quick while I've got your attention is that if I can find it. There we go. So doodling, I'm sure there's a better way to do this. One of my pet peeves about SolidWorks is that although you can have this curved flange of the metal tool, which is really nice. That's a curved flange, by the way. Ooh, yeah, fancy. We can't extrude a spline, so our top skin, which is a spline, is pieced together of 1 inch sections, which is kind of silly. I'm pretty sure there's a way you can convert to sheet metal from a surface. I don't exactly know how to do it. I don't know if you can do it actually, but this is somewhat acceptable for now. Thermal expansion is going to be about the level of loss that we would consider with something like this. So that's pretty much it. Obviously, everything will be redrawn several more times because a lot of the learning experience is failing and trying again and trying again and trying again. But I just wanted to give you a quick update of how everything's going, learning how to draw in SolidWorks, because that's really what this project is about. It's learning how to use SolidWorks. For closing remark, just want to say there are people out there who tell you that you shouldn't try and shouldn't you shouldn't be drawing things until stuff is done. And this is the part where I say that's the whole point of parametric CAD. You have parameters that you give it. So if you change your mind later, you can update the parameters. That's the whole point of parametric CAD. Parametric CAD. So there's nothing wrong with trying, failing, and learning, as long as you're willing to accept that you're gonna have to go back and redo it later. But that's progress, and thanks for staying tuned. Hope to get more people interested, word of mouth, because I'm not doing much anything better right now. So if you have questions, comments, reach out to me. Love to hear. Thanks for your attention. Have a great day. Bye.